In this lecture, I want to introduce you to a very interesting class of methods called the Condorcet consistent methods. So as a reminder, recall that the Condorcet winner is a candidate that is strictly preferred to every other candidate by some majority of voters. And we've seen an example, the so-called Condorcet paradox, that shows that such a winner may not always exist. So there may not always exist a Condorcet winner given the linear rankings of all of the voters. Now, a Condorcet consistent voting method is a method that always elects the Condorcet winner if one exists. And we've seen already examples of at least two methods that are not Condorcet consistent. So for example, plurality rule may not elect a Condorcet winner if it exists, and also Borda count, of course, doesn't elect the Condorcet winner even if one actually exists. But what we want to study in this lecture are methods that are Condorcet consistent. So in order to study these methods, I want to introduce what's called the majority graph. And this is a graph in the sense that computer scientists talk about graphs. So when a computer scientist thinks of a graph, they typically have in mind a set of vertices, so a set of nodes or dots, and then edges or links between those different nodes. So in a majority graph, the vertices are the candidates. So in this case, there are 4 candidates in the selection, A, B, C, and D. And we're going to draw an edge from one candidate to another candidate. It'll be a directed edge, so an arrow, if the first candidate beats the other candidate in a head-to-head election. So for example, we draw an edge from candidate A to candidate B because 26 people prefer A over B, but only 24 people prefer B over A. So the edge from A to B means that a majority prefers A over B. We see that there's a majority that prefers A over C, and a majority that prefers D over A. So we draw an edge from D to A. So we can fill in this graph by just looking at all of the pairwise comparisons. And I'll just flash through this quickly. You might want to pause to make sure you understand why I'm adding an edge in each case. So there's an edge from B to C. From B to D, there's also an edge. And then finally, from C to D, there's an edge. So this is the majority graph. And this is just simply a graphical way or a way to picture the majority relation that we've been talking about earlier. Now, we can already tell just by looking at this graph, by the structural properties of the graph, that a Condorcet winner doesn't exist. And the reason for that is there exists a cycle in this graph. So there's a cycle from A to B, B to D, and D to A. Of course, just the existence of one cycle doesn't tell you that a Condorcet winner doesn't exist, because maybe there's some other candidate that is strictly preferred to everybody that's within that cycle. But in fact, that's not the case in this data. We can see there's another cycle from A to C, C to D, and D back to A, and you can come up with an example of a cycle that involves all 4 of the candidates. So in fact, in this data, this is an example of a Condorcet paradox. There is no Condorcet winner. So what should we do? So the Condorcet consistent methods, one way to do this is to just simply say, this is what you might call Condorcet's rule, is to say that if a Condorcet winner doesn't exist, then just simply say everybody else is tied. So it's a way of just saying, well, I can't make a distinction between any of the voters. If a Condorcet winner doesn't exist, I don't know who to select, so we'll just have everybody else be tied. But you might be able to further distinguish between these 4 candidates, even in cases in which the Condorcet winner doesn't exist. And so the general idea is we want to find a candidate that's as close to being a Condorcet winner as possible. And the methods differ in how they understand what it means to be as close to the Condorcet winner as possible. One approach is so-called Copeland's rule. And this is an approach where we're asked to calculate for each candidate the win-loss record for that candidate. And that's going to be the number of candidates that you beat by a majority minus the number of candidates that beat you by a majority. So we can read off the win-loss record for each candidate by simply looking at this majority graph. So the win-loss record for A is going to be 1, and I can see that very easily because there's 2 edges going out from vertex A and 1 edge coming in. So if an edge comes in, that means somebody else beat you. And if an edge is going out, that means you beat that candidate that you can see. So in this case, there's 2 out edges minus 1 in edge. The win-loss record for A is 1. Same thing for B. There's 2 out edges minus 1 in edge. So the win-loss record for B is 1. For C, the win-loss record is -1 because there's 2 in edges but only 1 out edge. And same thing for D. There's 2 in edges and only 1 out edge. So since A and B maximize the win-loss record, they will be declared the winner. So they tied for winning the Copeland rule. Duncan Black proposed an interesting way of resolving the situation when there's no Condorcet winner. His idea is that you simply move to Borda count. So if there's no Condorcet winner, then Black's rule tells you to use Borda count to calculate the winner. We won't go through those calculations here. You might want to pause the video and make sure that these calculations are correct. But we can see that B ends up with the highest Borda score. So according to Black's rule, B will be declared the winner. Let's look at one more method. This is the so-called Dogson's rule. Named after Charles Dogson, who many of you probably will know as Lewis Carroll, the author of Alice in Wonderland. So Dogson did some interesting work on voting theory, and his rule asks you to somehow change this election, manipulate the rankings in the election, and do it in such a way that one of the candidates is turned into the Condorcet winner. But Dogson wants you to have some restrictions on how you're allowed to manipulate the data. So what you're allowed to do is you're allowed to make pairwise swaps between some of the candidates. So for example, you're allowed to swap this candidate B with candidate A. So make B the winner in one of these orderings, or you're allowed to swap if you want candidate A with candidate B or candidate B with candidate D. So you're only allowed to make pairwise swaps. And Dogson wants you to look for the fewest number of pairwise swaps that are needed to make that candidate the Condorcet winner. So in order to calculate the Dogson rule, we really need to run through a lot of calculations. So for every candidate, we need to figure out how many swaps, the minimal number of swaps you need in order to turn that candidate into a Condorcet winner. Well, we're not going to go through all of those calculations here. I'm just going to tell you that in this case, candidate B is the Dogson winner. And the reason is you can take 2 candidates or 2 voters from this first collection of voters and allow them to swap B with A. And if that's the case, we see now that once you do that, 26 people will prefer candidate B over A, but only 24 people prefer A over B. So candidate B ends up being the Dogson winner. It just so happened that this was the same as the winner declared under Black's method, but this is just an accident of this particular example. We can find many examples where the winner under Black's method and the winner under Dogson method are not actually the same. All right, so Peter Fishburne has studied all of these Condorcet consistent methods and proved a number of very general and interesting theorems about them. And one of the interesting things that you can find in this paper is a way of characterizing different types of Condorcet consistent methods. So the first class or type of methods that Fishburne wants to identify or categorize together are those methods from which the winners can be computed by simply looking at the majority graph alone. So in order to calculate the winner, all you have to do is look at the majority graph. So for example, the Copeland method is an example of a Condorcet consistent method that falls into this class. The second class of methods are those in which you need a little bit more information, namely you need to look at what's called the weighted majority graph. Now, the weighted majority graph is a majority graph in which you label the arrows, and you label the arrows with the advantage for the winning candidate. And the advantage is simply the difference between the number of candidates, the number of voters that prefer that candidate over Y minus the number of voters that prefer the other candidate over the first candidate. So we see that 26 people prefer candidate A over candidate B, but only 24 people prefer candidate B over candidate A. So we weight that edge with the number 2. That's the difference of the number of 26 minus 24, of the difference between 26 and 24. So that's the weighted majority graph. And finally, if a Condorcet consistent method does not fall in category 1 or category 2, then you put it in category 3, and Dodson is an example of a method that falls in category 3 because you need to look at you need more information than simply the weighted majority graph. You need to go back to the original data and figure out how can you manipulate that original data in order to make one of the candidates the Condorcet winner. Peyton Young also proposed a similar method where you don't change the orderings, but rather ask how many voters can you remove from the election in order to make the candidate a Condorcet winner. And so that also is in a method that falls into this third category. So these are a number of Condorcet consistent methods. All of them, they're mathematically very interesting, a bit more sophisticated than the other methods we've looked at. And these will provide us with a number of examples that we'll return to when we study more general properties of voting methods.